I'll be right with you, gentlemen. No copyright gaming background music. All right, gentlemen. So let's see. Hope everyone is doing well. Hope everyone had a great weekend. Enjoyed your homecoming. Did we win? I didn't even bother to try to get involved with any of the festivities. Did we win the game? Did you all enjoy your homecoming? Did anybody have any interest or did they like to share? Just curious. Let me see. Yeah, so no real announcements. We're just gonna continue on with the next installment. All right. So I think last time we did section 2.1. I think it was like rational functions. I think I don't even remember, to be honest. Let me see. Can I just see the name? Let's go. Rational functions, yeah. Polynomials and rational functions. That's fine. Okay. So, and let's go to view. Single page. Okay. So we're continuing chapter 2 on polynomials and rational functions, and we're going to focus on polynomial functions. A few objectives here. One, learn the properties of the graphs of polynomial functions. 2, determine the end behavior of polynomial functions. 3, find the zeros of a polynomial function by factoring. 4, identify the relationship between degrees, real zeros, and turning points. And 5, graph polynomial functions. So we'll get through as much of this together as we can. As usual, whatever we don't finish together, I do expect you to use my pre-recorded lectures to fill in the gaps. So we're going to open up with some definitions. Let me see. A polynomial function of degree n is a function of this form, where n is a non-negative integer and the coefficients an minus 1, all the way down to a1 and a0 are real numbers where an is not equal to 0. All right. So we're introducing what do we mean by a polynomial. I like to describe a polynomial as a finite sum of monomials. And a monomial is going to be kind of like a power function where you have some real coefficient times x raised to a non-negative power n. All right. So then once you're clear about what a monomial is, then a polynomial is just a finite sum of monomials. All right. Let me see what we got on the next slide. The term an x to the n is called the leading term. The number an is called the leading coefficient, and a0 is the constant term. A constant function f of x equal to a, where a is not equal to 0, may be written as f of x equals a times x to the power of 0. This is going to be a polynomial of degree 0. So then, again, in polynomial functions, we have the leading term. The leading term is the term with the highest power. So when you have your polynomial listed out, the leading term is the term with the highest power. And then the constant term is, usually the term without, it's just a number, no variable, right? And then we also have this notion of a zero function, right? So if we have f of x equal to 0, we say that this has no degree assigned to it. And we say this because it can be written in an infinite number of ways. Like if f of x equals 0, but then that's the same as like 0 times x squared, but then that's the same as 0 times x to the 100, right? Because 0 times anything collapses to 0. So whenever we have f of x equal to 0, we call that, we say that has no degree assigned to it. Okay. Polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic polynomials. So this expression we call a polynomial, all right? So this first line is an example of a polynomial expression. And then a function defined by f of x equal to that polynomial, we call that a polynomial function. And an equation where we have the polynomial expression equal to 0, we call that a polynomial equation. Okay. A few properties of polynomial functions. The domain of a polynomial function is a set of all real numbers. Okay, that's pretty straightforward. The graph of a polynomial function is a continuous curve. So for instance, on the left, we have a continuous curve, meaning we can start at any point on the graph and get to any and start. We can get to any other point on the graph by tracing the graph without picking up our pencil. So there are no holes or gaps, or breaks in our graph, right? So continuous, no holes or gaps or breaks, as in the example on the right, right? So we have a hole or a gap. So if we started on the left-hand side and we started trying to trace the graph to get to the right-hand side, we'd have to pick our pencil up and jump over that gap, to kind of continue on. So that's an example of something that cannot be the graph of a polynomial. So again, property number 2 is that the graph of polynomials are continuous, no holes or gaps or breaks. And then the graph of a polynomial function is a smooth curve, right? So the image on the left, notice it's our curves are smooth, there are no holes or gaps or breaks, versus the image on the right, we have those sharp corners. So if an image or if a graph has a sharp corner or edge or anything like that, then it can't be the graph of a polynomial, right? Okay. So again, the main takeaway from these 3 properties, in general, the domain of a polynomial is going to be all reals. The graph of a polynomial is going to be a continuous unbroken curve, a continuous unbroken graph where our curves are smooth, so no sharp corners, edges, or anything of that nature, or holes or gaps or breaks. So state which functions are polynomial functions. For each polynomial function, find the degree, the leading term, and the leading coefficient. Okay. So notice that in A, we have a finite sum of monomials, right? This is a trinomial. The first term, or our leading term, let's just say the first term, is going to be the 5x to the power of 4. Our second term is at negative 2x, and the third term is at 7. Let me see. Then we're asked to find the degree, the leading term, and the leading coefficient. Sorry. We're asked to find the degree, the leading term, and the leading coefficient. So the degree of a polynomial is going to be the highest power on any term, right? So in A, the degree is going to be 4. And then the leading term is the term with the highest power. So the leading term is going to be the 5x to the power of 4. And the leading coefficient is going to be the coefficient of the leading term. So in this case, it's going to be 5. Okay. And then for B, normally that would be a polynomial, but we have a restriction on the domain. So because of that restriction on the domain, that can't be the graph of a polynomial function. Okay. And I think we have all that typed up here. Okay. All right. So we have this notion of what we call a power function. So a function of this form is called a power function of degree n, where a is a non-zero real number and n is a positive integer. So this is essentially a monomial, right? Our a is a non-zero real number, n is a positive integer, right? Okay, let's keep going. I can't think of anything else there. So given a power function, if the degree of the power function is even, or if n is even, then we have negative x quantity to the power of n equals x to the power of n, right? So what we're saying is that if our n is even and we evaluate f of negative x, then we're going to have a times negative x to the power of n. But then a negative number to an even power becomes positive, right? So we're going to have 8x to the n, which is the original f of x, right? So we're starting with f of negative x and we're finished with f of x. That's the definition of a function being even, right? F of negative x equals f of x. That's the definition of a function being even. So then if it's even, that means the graph is going to be symmetrical with respect to the y-axis. And so the graph of y equals x to the n, where n is even, is similar to the graph of y equals x squared, right? Okay. So that's if n were even. Then naturally, we would want to explore, well, what if n were odd, right? So then, so given the power function f of x equals ax to the n, if n is odd, then negative x to the n is going to be a negative times x to the n, right? So negative x quantity to the power of n is equal to a negative times x to the n. So in other words, what we're saying is f of negative x if we replace x with negative x, we're going to get a times the quantity negative x to the power of n. Because n is odd, that means the next line is going to be negative ax to the n, right? And then, but that's the same as a negative times f of x. So we started with f of negative x. We finished with negative times f of x. That's the definition of a function being odd, right? If that negative weren't there, that the second negative, if it were equal to f of x, like in the previous slide, again, that's the definition of a function being even. Here, f of negative x equals a negative times f of x. That's the definition of a function being odd. So then from properties of the odd functions, it's going to be symmetric with respect to the origin. All right, so that means that whenever we have x comma y, we also have negative x comma negative y. The graph of y equals x to the n, where n is odd, is similar to the graph of y equals x cubed. All right, so another way to kind of conceptualize or visualize an odd function, whenever we have x comma y, we also have negative x comma negative y. So it's like a double negative. The shape kind of makes like an S pattern where all the points are symmetric about the origin and symmetric and equidistant about the origin. So it's like they're dancing around the origin almost. Okay, so if we were to consider the n-graph behavior of our power functions, right? So I want to say something is missing here. Let's see. N is even.
My son, my son.
If you have a question, going once, going twice. All right, sorry. Okay, so again, we want to explore in behavior of a polynomial function. This first case where a is positive, right, and n is even, right? So a is the leading coefficient, right, or in the power function. If we have if the a is positive, that tells us that the right-hand side of the graph goes up. So as x goes off to positive infinity, y tends to positive infinity, okay? So again, a positive leading coefficient or a positive a in this context, as x goes off to the far right, our y value tends to positive infinity. When n is even, that tells us about the other side of the graph. Even power function means the other side does the exact same thing. Even means the exact same. So as x goes to negative infinity, y goes up, or y tends to positive infinity. Okay. So again, we start with our leading coefficient, our a. If it's positive, y we go up to the right. If it's negative, we go down to the right. So on and so on. Even power function, the other side is the exact same. An odd power function, the other side does the opposite. Okay. So in case 2, our a is negative. Notice we're going down to the right. So as x goes to positive infinity, y tends to negative infinity. Again, here, our n is even. Our n is even. So that means the other side does the exact same, right? Even means exact same. So if we go down to the right, we're also going to go down to the left in this case. Okay. So then case 3, paste. Okay. So now our leading coefficient is positive, but now n is odd. So again, a positive a means we go up to the right. But now the degree is odd, that means the other side does the opposite. So if we're going up to the right, the other side is going to go down to the left. Right? So, it's kind of like being symmetric about the origin, that kind of S pattern we were kind of talking about. Right? And then lastly, when our a is negative and n is odd. A is negative and n is odd. So then a negative a we're going to go down to the right. Because the degree of our power function is odd, the other side does the opposite, so we're going to go up to the left. All right? Okay, that's fine. Let's keep going. All right, so given this polynomial function of degree 3, we're asked to show that this polynomial is approximately equal to 2x cubed when the absolute value of x is very large. Okay. Oh, make sure you guys are okay. In the module. Give me just a moment. Let's see. Ooh. Okay. So let's start with the polynomial. All right. So we're going to start with p of x, which is what? 2x cubed plus 5x squared minus 7x plus 11. And then here, what we like to do is factor out x cubed from all the terms. I'll do it here. Okay. If we do that, that's going to leave us with 2 plus 5 over x minus 7 over x squared plus 11 over x cubed. Okay. So now what we like to do is let the absolute value of x tend to infinity. So what happens is we let the absolute value of x get really, really large. Okay. So now, if we were to focus on this second term here, it is 5 over x, right? What happened? Well, let's choose a few test values, right? So for instance, when x is 1, what's that output, right? Just think about what that answer. If we say 5 divided by 1, what's that output? And then think about 5 divided by 2, what's that answer? Think about 5 divided by 5, what's that answer? 5 divided by 2 by 50. 5 divided by... Notice that as that denominator gets bigger and bigger and bigger, that expression itself gets, hopefully you're thinking, smaller and smaller and smaller. So as the absolute value of x tends to infinity, this guy gets closer and closer to 0. If you can understand that dynamic in that term as the absolute value of x tends to infinity, then it's a similar argument for this one and this one, right? So because we have a fixed number over an ever-expanding denominator, those guys essentially go to 0. So now it's like we have 2 plus 0 plus 0, right? So then at this point, we can say that p of x is approximately equal to x cubed times 2 plus 0 plus 0 plus 0, which is 2x to the power of 3, right? So what we're saying here is that this polynomial, as x tends to positive infinity, or as the absolute value of x tends to positive infinity, essentially behaves like the power function 2x cubed, which is the leading term of the polynomial, right? So long story short, those 4 cases that we just had for the power function, we can actually extend it to polynomials in this concept called the leading term test for polynomials, right? So what we did there was fine. And so that leads us into this notion or idea that we have called the leading term test. So given a polynomial where the leading coefficient is not 0 and the leading term is a(n) x to the n, the behavior of this function as x tends to either positive infinity or negative infinity Negative infinity can be shown in a similar fashion like we did positive infinity. So the behavior of this graph is x either goes to either positive or negative infinity is going to be similar to one of the following four graphs and are described as shown in each case. The middle portion of each graph indicated by dashed lines is not determined by this test. So what this test is going to show us is how the graph behaves in the long run. It doesn't give us any information about the middle. It just tells us, as x either goes to positive infinity or as x tends towards negative infinity, right? Okay. And let me see. Paste. Come on. So our leading coefficient is positive and n is even. Okay. So similar to the case one for the power function, again, a positive leading coefficient means what? We go up to the right. When n is even, that means the other side does the exact same. So we're going to go up to the right, up to the left. We don't know what happens in the middle, but we know that in the long run, the graph goes up to the right and up to the left. Okay, so that's a positive leading coefficient. Now we look at a negative leading coefficient. All right, so a negative leading coefficient, our graph is going to go down to the right. N is even, the other side does the exact same, so we're going to go down to the left. Okay. Okay. So it's basically, it matches the power function. It's just that we don't really, this doesn't give us information about the middle. It just gives us information about the long term. Okay. So then in this one, delete. So n is odd, right? Okay. So we have a positive leading coefficient and n is odd. A positive leading coefficient means we go up to the right. N is odd means the other side does the opposite. So we're going to go down to the left. Okay. No information about the center right now, but we know it goes up to the right in the long term, down to the left in the long term. And lastly, A is negative where N is odd. Delete. So A is negative, a negative leading coefficient. We're going to go down to the right. N is odd. The other side does the opposite. So we're going to go up to the left. Okay. So hopefully we're all aboard or we're not all aboard. I know this stuff can be dry. This is a challenge that, that we have to overcome. I do my best to try to breathe life into it. Again, as best as I can. I know I've been a little bit redundant there. I'm a little bit like under the weather. I don't know. It's just weird. I feel weird, but I got my little tower, so I'm up trying to raise energy a little bit, Okay. Because Lord knows if I were sitting down, I'm already looking down. The body goes where the head will follow. The head goes where the eyes follow. So I try to counter it a little bit. It's a little tug of war, a little bit of internal battle because I'm looking down, but I'm standing up. So, and I'm constantly like looking up, trying to just bring energy up. Right. So that's just a little, again, the whole changing your physiology, your body position to change your energy. Okay. Like if you're not feeling well, just get up, basically, and you'll feel better. Get up, go for a walk, stuff like that. Okay. So here we're actually use the leading term test to determine the end behavior of the graph, okay? Right? So the leading term, right? So the leading term is the term with the highest power. Let me think. Let me think how I want to do this. I kind of do want to do this real quick. Okay. Let me see. We're going to say quick quiz. Okay. So the first question. What is the leading term? Okay. Is it A, 3x squared? Is it B, let's go 4, or is it C, negative 2x cubed? Right, we're coming up with that. That's coming. Okay. Question number 2. What is the leading coefficient? Let's go A, B, or C. Let's see, 3, 4, or -2. That's fine. Okay. I'm going to try this last one. The last one's going to be a little intense. Okay. It is the third question. What is the long-term behavior of this polynomial function? Okay. Let me see. So we got A. We'll go, let me see, up to the right and up to the left. B, up to the right and down to the left. C, down to the right and down to the left. Or D, down to the right and up to the left. Okay, that's our quick quiz, right? So you can, hopefully you already got answers lined up. I'm going to do my little poll. I know last time we had an adventure with this thing, so I'll give you a little update. So I know we kind of did, like on Wednesday, we did like a little interactive thing that you were responsible for attendance. So since I had so many like hiccups and it wasn't polished, as long as you showed any signs of life, you were either here or you answered questions, I generally gave people credit. Like I didn't be super staunch, but going forward, I probably will do something like that. So when I start asking doing the polls, I need you guys to engage. If you're not engaged, to me, that's going to say, hey, you're not really here. Then you could potentially not get your attendance credit for that day. And you know that whole narrative. But it's still real simple. And I'm only giving credit to those that get it right. So you got to get it's at least 50%, right? You know, so that's probably how our Wednesdays are going to go. Let's open this up. We want to do the 25 question poll quiz because we're just going to use the first 3. Right. So so there is a poll that's active. Let's take, matter of fact, like this so we can see a little bit better. Come on, there you go. Let's take a minute and a half, right? So when we get to 2 minutes on the little timer, we'll close it out. So just take a moment. It shouldn't take that long. But we're going to take about a minute and a half. And I'll tell you how to close it out, how to submit it. Once you got to answer all 3 questions though. So question 1, question 2, question 3. And then once we do that, I'll tell you how to close it out. Matter of fact, I'll go ahead and do it on my end as well. I need to join this one. That's fine. Audio join. So we still got about 50 seconds. Leading term is okay. That one, that's fine. And okay, so okay. Let's take about 20 more seconds and I'll tell you how to submit it. All right, so that's time. Okay, so hopefully you've at least highlighted your correct answers. Again, in order to submit, you scroll down to the very bottom and you got to answer the last 2 questions. So are we at the last minutes of the class? You could just say yes. And then how do you feel about the result? It's just a rating on how you feel. Where 10 is you're confident, 0 is like, dear Lord, dear baby Jesus, please, I need some help, right? Okay, so I'm gonna hit submit. Okay, so again, I'll just take a little bit of time. So go ahead and submit. It's at the very bottom. Again, you have to fill out those last 2 questions. I'll give you another 15 seconds to get those in. We got, let me see, 33%. We need better participation than that. Okay, you guys are coming through. I can see you. A little bit more, a little bit more. Let's go, let's go. Let's go, let's go. Encanto, man. That movie. Encanto, Coco, Soul, and Disney has some bangers. Like, I know they seem like whatever, but man, those are some fun movies if you haven't checked them out. A few more. We still got about 7 people. So you want to make it a habit of being engaged. Because I'm gonna start sooner or later. I'm gonna start counting these, and you don't want to be docked for free stuff. Okay, I'm gonna go ahead and close the poll. Forever, forever hold your peas and rice in 5, 4, 3, 2. Can we get one more in there? That's okay. We're good. All right, let's close the poll. All right, good, nice. Okay, we got some feedback here. Okay, so this is interesting. I'm glad we did this. All right, so I'm going to assume that everybody's sincere. I mean, I would imagine so. I don't see why it wouldn't be. So let's go through this quiz. All right, let me think. How do I want to do this? Let's go chill like this. Let's do like chill. That's decent, I guess. Let's go style. Stroke can be like this, a little bit thicker than a Snicker. Oh, we're not necessarily done. I wouldn't dip out. That is not a good look. But it's okay. What's the time? We still got a solid just 10 minutes. We can hang out for 10 minutes, right? So the leading coefficient, right, is determined with the highest degree. The highest degree in this case is a 3. I intentionally tried to jumble it up. I should have jumbled up the second one. So C was the correct one for the first one. So I know we got at least one, but that's okay. This is why we're doing this, right? We just need to, kind of get that. Okay, then for question 2, let's duplicate. What is the leading coefficient? So it just matches up. So it's kind of like a twofer. If you get one, you get the other, kind of by default, right? So the leading coefficient in this case was a -2, right? So that piece of information, we needed that to answer question 3, right? The leading coefficient is negative. That means we should be going down to the right. Oh, another question I could have asked is what's the degree of the polynomial, right? We got the leading term, we got the leading coefficient. We could have also talked about the degree, right? The degree of this polynomial is the highest power on any term. The highest power in this case is a degree 3, right? So, which is odd. So then, and don't confuse an odd degree with an odd function, right? An odd degree means the highest power is an odd number versus an odd function that has to satisfy that f of negative x equals a negative times f of x. So those are two different concepts. Very subtle. They sound really similar. So then the result for part C, if we have a negative leading coefficient, it should go down to the right. If the degree of the polynomial is 3, which is odd, that means the other side does the opposite, so it should go up to the left. So the only option that goes down to the right and up to the left is D. Let me see, how do we do? Okay, I think we got a little bit more, caught a little bit more off guard with that one, right? Yeah, I think D was the only one that goes down to the right and up to the left. Okay, so not bad, not bad. Just some feedback, trying to, again, pump some energy into you guys, because I know how dry this stuff could be. But see, it's coming together, right? We did our little quiz last time. I was like, okay, I had to work out the kinks. I realized that I needed to lock it, have some kind of way to stall you guys from submitting it, because I think originally, we tried to submit it and it just threw everything off. I was like, damn. Can't even laugh. I hate that. I hate when I like sick and I can't laugh and it makes me cough. So then it makes me want to laugh more, which makes me cough more. And it's like this vicious cycle until I just have to intentionally make myself stop laughing. Anywho, that happens periodically. Okay, so that was a fun little whatever. We only got 5 minutes. Well, no, actually it's more like 10 minutes, but I know it was 10 minutes 5 minutes ago. I'm just trying to distort time a little bit. Okay, anyway, that was fun. Okay, so the degree is the only thing we're missing there, but that's fine. Oh, typos here. So let me suppress this quiz for right now. So that was fun. Okay, I need to do my attendance from this morning. I guess I'll do that after my next class. Let me get rid of the typos here. So these little R's, those are just where the symbol didn't process. Sometimes the symbols don't show up properly. I think those are just like right arrows. So what what I did before. Copy and paste. I can just blot them out. Like that. Copy, paste, paste, paste. And then let's do like this. Style, step by one. It's too low. All right, that's decent. Duplicate. So those are really just supposed to be right arrows. Duplicate. Ended up seeing Smile too. Yeah. It was a weird movie. I mean, I wasn't bored, I'll say that. I didn't see Smile 1. I was glad I saw it, but I don't know. It was a weird movie. It was okay. Give it maybe a 6.7 out of 10. You know, like I think I would have been okay if I didn't see it, but I was kind of indifferent about it, to be honest. But if you wanted to see it, I would encourage you to see it. If not, then you'll be okay not watching it. Oh yeah. So this was just a type version of what we experienced with that last example. Okay, that's fine. I'm gonna let that stuff be. Okay, so real zeros of a polynomial functions. If f is a polynomial function and c is a real number, then the following statements are equivalent. One, c is a zero of f. Two, c is a solution or root of the equation f of x equal to 0. C is an x-intercept of the graph. The point c, zero is on the graph. So these three expressions or statements can be used interchangeably. So whenever you hear us say the x-intercept, that's the same as saying c is a solution or root of f of x equal to 0. And that's the same as saying that c is a zero of the function, right? So these three notions we use interchangeably. Okay. For the sake of time, I'm going to have to leave this as an exercise. So I would have to encourage you to like use my pre-recorded lectures to kind of watch this, because this same example is worked out there, and we have it typed here. So I'm going to have to piggyback off of that. So the intermediate volume theorem, let a and b be two numbers such that a is strictly less than b. If f is a polynomial function such that f of a and f of b have opposite signs, then there's at least one number c between a and b for which f of c equals 0. So this is a play on the properties of polynomial functions, that the domain of a polynomial is all reals, that polynomial graphs are continuous with smooth, unbroken curves. So then if we have two different x values and the corresponding y's have opposite signs, then there has to be a c between those two different x values. That's basically an x-intercept where it crosses the x-axis. That's the intermediate volume theorem, right? And we kind of see it in action here. Two different x values, the y's have opposite signs. So our polynomial graph crosses the x-axis somewhere between those x values. The x-intercept is somewhere between those x values. And it may be more than one x value between as well. Okay. So in this example, we wanted to show that it has a real 0 between these two x values. So we would evaluate this function at these x values, show that they have opposite signs. And then by the intermediate volume theorem, because this is a polynomial, there has to be some 0 between there. And we can estimate it. I think I go through those details in the recording. So I'm going to, again, this is one I'm going to have to refer you to my recording for the details. And also we had a typed version of the solutions there. Let me check here. Okay, you guys look okay. A polynomial function of degree n with real coefficients has at most n real zeros. So once you identify the degree of the polynomial, you have at most that many zeros. Like quadratic, which is the highest power is 2, we have at most 2 zeros. You're not guaranteed 2 zeros, but you're guaranteed to not have more than 2 zeros, right? So we have at most that many number of zeros. I'm going to have to defer you to my recording for this one. Multiplicity. If c is a zero of a polynomial function f of x and the corresponding factor x minus c occurs exactly m times, when f of x is factored, then c is called a zero of multiplicity m. If m is odd, the graph of f crosses the x-axis at x equals c. If m is even, the graph of f touches but does not cross the x-axis in c, so it's going to bounce off the x-axis. All right, so like, again, if the multiplicity is odd, it crosses the graph. If the multiplicity is even, it's going to bounce off the x-axis. All right. So for instance, in this example, we're asked to find the zeros and give the multiplicity of each zero. So we have like a total of 3 factors. Factors are things that we multiply and divide, or things that we essentially multiply. So then x squared, right? That's the first factor. And that zero is going to be when x is 0. That's the example where that multiplicity is 2. But then the factor x plus 1 has a multiplicity of 1 because it has a power of 1. And x minus 2 has a multiplicity of 1 because it's a power of 1. Again, those details are in my recording. So, and it's a type version here that goes into more details. And then a local max or a local min. The local max is going to be like the peak of a mountain, right? So we have our polynomial curves. When we have like a turning point and it's the top of a mountain, we call that a local maximum. And then the local minimum is like the bottom of a valley. So when we have our polynomial functions, when we have those dips, those bottom of the valleys, that's what we call a local minimum. The graph points corresponding to the local max and the local min are called turning points. At each turning point, the graph changes from either increasing to decreasing or vice versa. Right, so on the left, we have a local max at negative 112. On the right, we have a local min at 2, negative 15. So these are the turning points, identifying the local max and the local min. If f is a polynomial of degree n, then the graph has at most n minus 1 turning points. All right, so whatever our n is, like say our n was 5, then we would have at most 4 turning points. We have at most 5 zeros and at most 4 turning points for that case. Okay, so I'm gonna have to defer to my recording for this one. This one as well. So I kind of want to give a brief overview of sketching the graph of a polynomial. And I'm going to kind of piggyback off of what we did for graphing rational functions, right? So first, we might consider intercepts. So x and y intercepts. My recommendation is to do the y-intercept first, whenever possible. I feel like oftentimes the y-intercept is easier to find than the x-intercept. X-intercept, a lot of times we got to do factoring or this, that, and the other. And sometimes that can be a little bit challenging. Y-intercept is usually really quick. You can almost just look at it and get the y-intercept. We might use our leading term test. So I'm going to abbreviate it as leading term test. Okay, so that tells us about the long-term behavior. We might do a test for symmetry. So that's to determine if the function is even, odd, or neither. So again, using those definition of even function. If the function is even, that means y-axis symmetry. If the function is odd, that means origin symmetry. If it's neither even nor odd, then there's no symmetry. For a few additional points. Between and beyond the x-intercepts. I think when we had rational functions, we did a few additional points between and beyond the x-intercepts or vertical asymptotes. With polynomial functions, we're not going to have any vertical asymptotes, so just between and beyond the x-intercepts. And then lastly, we just want to graph or put all these notions together. I might go through some additional details in the recording, so you definitely want to check this out to see this in action. These can be a little bit involved, but just do the best you can. And I'm also going to use my recording for this one. Are there any burning questions before we go our separate ways? Going once, going twice. Forever, hold your P's and rights. Let me see. So on Wednesday, more than likely, here on out, for our Wednesdays, we'll do our homework sessions, and we'll use the polls as attendance, right? So if I'm doing polls, the only way you can get credit is if you get them correct. I'm working out those details, so I'll be less and less lax about it, right? So Wednesdays are less and less passive. I want you guys to be a little bit more engaged, and not just like if you get them wrong, then Again, you got to get at least 50%, but we'll save that for Wednesday. If there aren't any burning questions, we're going to go ahead and end the session here. From one beautiful mind to another, enjoy the rest of your evening, and we'll meet back on Wednesday, same time, same place for the next installment. All right, gentlemen, take care. Peace. All right, let me go ahead and share this before I leave.
I have a question.
Yes.
For the attendance quiz last week, if you weren't able to get 100, is your final grade it? Or like, what if you had like technical difficulties? Can you?
I was kind of lax last week. Like, as long as you show any signs of life, so it's like either if you were here, or if you attempted, or if you reached out, as long as you show any signs of life, I essentially gave you credit.
Or I'm talking. It's on the Pearson the lab. Because like I got like 50, but I was like still doing it, and then like had that cut out. So
You
like,
talking about what we did in class? Those like attendance quizzes.
yes.
You can see your attendance grade. So one, attendance doesn't affect your grade. It's just for attendance. It only really becomes an issue if like you rack up through like more than 3 unexcused absences. So it doesn't affect your grade. This is just for attendance, and again, it's only an issue if you're like marked as absent, unexcused, like 4 more times. But you can see your attendance grade on Blackboard. Right now, don't worry about it. Really, as long as you're showing up on a regular basis, you're getting your stuff submitted. I'm not gonna boot you because of attendance. If attendance becomes an issue, just as long as you have evidence that you've been here, you've been submitting your stuff, then I'll make a case for you to stay. So we'll figure out a way so that it doesn't hold you back. You just don't. There are sometimes people are MIA, like no show, no call. Then you know, then those are the ones we're trying to boot out. But if you're regularly showing up, submitting your assignments, and you're making the effort and you say, hey, I'm trying to finish, then usually I'll make sure that you are able to stay in there. So I would say just check it on Blackboard to just see. And if you see a day where you were trying, if you can show like evidence of whatever was going on at that time, then I'll retroactively probably like mark you as excused. But you can see those details in Blackboard.
Okay.
Okay.
Thank you.
All right, gentlemen. Any other questions? Okay. So I'm going to stay on the call. I'm just going to. Oh, I meant to change that. I forgot to change it in my title. Let me check here real quick. That's okay. I think we got it. I closed that pool is closed. Okay, guys. So I'm going to kind of stay on the call, but just because I have another class in like 10 minutes. Otherwise, I'll see you on Wednesday. I'm going to mute myself.
Streets are empty. The only thing I can see is my own silhouette. I'm getting stronger, step by step. The clock is ticking, but there's no time for peace. I've been flying from town to town, from mountain to town. Been all around the globe, trying to protect your soul.
Siri, set a timer for 2 minutes.
2 minutes starting now.
I almost said 20 minutes. That's why it sounded like.
Ready to explore right up in the sky. I need you to listen, I need you to hear. And don't show any fear. I've been flying from town to town, from mountain to the south. I've been all around the globe, trying to protect your soul. We are heroes tonight. We fly above the sky. We are heroes tonight. We are heroes tonight. We fly above the sky. We are heroes tonight.
Siri, stop. All right. Welcome, gentlemen. Let me see. So no real announcements. Hope everyone had a great weekend. Did we win the homecoming game? I don't know. I didn't even bother to get engaged. Did you all enjoy your homecoming? Anybody do anything interesting? I just took a friend to see what is that movie? Smile 2. It's a weird movie. Let's see. Are you in the digital campus? Okay. All right. Anywho, so let me make sure this my audio is working. I know that's working. Yeah, that's working. Okay. So we're just going to continue where we left off. So we were working on chapter 2. I think last time we did polynomial functions. Sorry, last time we did rational functions. So today we're going to be working on polynomial functions. Section 2.2 polynomial functions. A few objectives here. 1, learn properties of the graphs of polynomial functions. 2, determine the end behavior of polynomial functions. 3, find the zeros of a polynomial function by factoring. 4, identify the relationship between degrees, real zeros, and turning points. And then 5, graph polynomial functions. Yeah. So we'll go through as much of this together as we can, and then whatever we don't finish together, I do expect you to use my recordings to fill in the blanks or the gaps. A polynomial function at degree n is a function of this form, where n is a non-negative integer and the coefficients are real numbers where an is not equal to 0. Another way I like to kind of summarize or conceptualize a polynomial function is as a finite sum of monomials. A monomial is going to take on the form where you have some real number coefficient times a variable x raised to a non-negative integer power. So again, that's a monomial. Things like 2x squared, 3x to the 7, 3, 5, 5x, stuff like that. Those are all monomials. So then a polynomial is just going to be a finite sum of those guys. Okay. So the term an exited is called the leading term of the polynomial. The number an is called the leading coefficient, and a naught is called the constant term. Right. It's usually the term without a variable x. A constant function f of x equal to a, where a is not 0, which may be written as f of x equals a times x to the 0, is a polynomial of degree 0. Right? So when we have f of x equals a constant number other than 0, we say that has a degree of 0. But then the 0 function f of x equal to 0 has no degree assigned to it. Polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic polynomials. Okay? So this expression we call a polynomial expression. Then the function defined by f of x equal to that polynomial expression we call a polynomial function. And then the equation where we have that polynomial expression equal to 0 is a polynomial. We call that a polynomial equation. Okay. So a few properties of polynomial functions. One, the domain of a polynomial function is a set of all real numbers. Okay, so in general, the domain of a polynomial is all reals. Another property. Okay, let me see. That's okay. All right, that's fine. Another property of polynomial functions are the graph. The graph of a polynomial function is a continuous curve. So if we're visualizing the image on the left, we can pick any point on the graph and get to any other point on the graph by tracing the graph without having to pick our pencil up. But the image on the right, if we started on the far left and started tracing the graph, in order to get to points on the far right, we would have to pick up our pencil to jump over that gap, and so the image on the right is indicative of a graph that's not a polynomial. So again, here, property of the graph of a polynomial is that the graphs are continuous. So there are no holes or gaps or breaks in the graph. Okay, if there is a hole or a gap or a break, then it can't be the graph of a polynomial function. Another property of polynomial functions is that it's a smooth curve, right? So on the left, notice that it's continuous. All our curves are smooth. So that could be the graph of a polynomial. But on the right, we have those sharp corners or edges. So if our graph has any kind of sharp corners or edges, then it can't be the graph of a polynomial function. Okay. So say which functions are polynomial functions. For each polynomial function, we're asked to find the degree, the leading term, and the leading coefficient. All right, I'll save that for later. So then for part A, right? In part A, we have a finite sum of monomials, right? The first monomial, this is a trinomial. We have 3 terms. So tri meaning 3, like the Tri-Wizard tournaments, Harry Potter. But we have this is a trinomial, so it's 3 terms, right? The first terms are things that we add and subtract. Factors are things that we multiply and divide. So the first term in this case is going to be that 5x to the 4. The second term is the negative 2x, and the third term is the 7. So in part A, we do have a finite sum of monomials, so that is a polynomial in part A. The degree of the polynomial is going to be the highest power on any term. So the degree in part A is going to be a degree 4. The leading term is the term with the highest power. So that's going to be, the leading term in this case is going to be 5x to the 4. And the leading coefficient is going to be the coefficient of the leading term, which is the 5 in this case. Okay. So A is a polynomial. Normally B would be a polynomial, but we have a restriction on the domain. The domain is restricted where x is between 1 and 5 inclusive. So because we have the restriction on the domain, that's not a polynomial function. Because remember, we just said that the domain of a polynomial function is going to be all reals. Okay, and so we have what we just experienced typed up here. So the same thing just typed up already. Okay. So then we move to this notion of what do we mean by a power function? Okay, so a function of this form is called a power function of degree n, where a okay. Where a is a non-zero real number and n is a positive integer, right? Okay, power function. It's a subset or a derivative of a monomial. I want to say that all power functions are monomials. Let me see. Yeah, but not all monomials are power functions. Yeah. So anyway, you don't really need to know all that. So given a power function, if n is even, then a negative x quantity to the power of n, if we're raising it to an even power, then the negative goes away and it becomes positive. So then if we evaluate f of negative x, we're going to have a times the quantity negative x to the power of n, but n is even, so the negative is gone. So now we have 8x at the end, which is the original f of x. So notice here we started with f of negative x and we finished with the original. I think from Monday, that's the definition of a function being even. Maybe not from Monday, from before Monday probably, last week. But we've talked about the definition of a function being even, right? So f of negative x equals f of x. That's the definition of a function being even. So an even function, the graph is going to be symmetric with respect to the y-axis, right? So whenever we have x comma y, we also have negative x comma y. The graph of y equals x to the n when n is even is similar to the graph of y equals x squared. So we have y-axis symmetry. Whenever we have a point on the right, we have a point on the left. And then we want to consider when n is odd. So if we consider the power function f of x equals ax to the n, where n is odd, then if we have negative x quantity to the power of n, because n is odd, we can rewrite that as negative x to the n, right? So in other words, the negative persists because the power is odd. So then when we consider f of negative x, that's going to be a times quantity negative x to the power of n. But because n is odd, we essentially can just like factor out that negative and it persists. And ultimately, we're going to finish with a negative times f of x. So we evaluated f of negative x. We finished with a negative times f of x. That's the definition of a function being odd. So odd functions, the graph of an odd function is going to be symmetric with respect to the origin. So in other words, whenever we have x comma y, we also have negative x comma negative y, okay? And the graph of y equals x to the n, where n is odd, is similar to the graph of y equals x cubed, kind of that S-shaped graph that we've kind of experienced. All the points are symmetric about the origin and equidistant. And again, whenever we have x comma y, we also have negative x comma negative y. Okay. So then if we consider the power function, and we have these four cases, let me see. I think I gotta write it again. No, pace, let's see for pace. That's not what I want. Okay, so in this case, we have a positive a, and our n is even. So, like if we consider the power function f of x equals ax to the n, that leading coefficient a is positive. A positive leading coefficient means our graph goes up to the right. N is even means the other side is the exact same. So we start with the a. If a is positive, we go up to the right. Because n is even, the other side does the exact same, so we go up to the left. Okay? So that's where a was positive. Now we want to consider when a is negative. Okay, and n is even. So a being negative means our graph goes down to the right. N is even means the other side does the exact same. So we're going to go down to the left. Okay. All right. So then the next one, now we're back to a being positive, but instead of n being even, now we want to consider when n is odd. Okay. So a positive a means what? We're going to go up to the right. N is odd means the other side does the opposite. So we're going to go down to the left, up to the right and down to the left. Okay. And then the last case, case number 4, where a is negative and n is odd. Okay. Negative a means we're going to go down to the right. N is odd, so the other side does the opposite. So we're going to go up to the left. Okay. So those are the n-graph behaviors of the power function, right? We saw the 4 different cases where n was even or odd with a positive a or a negative a, and how that affects the long-term behavior. So now in this example, we want to consider, given this polynomial function of degree 3, we're asked to show that this polynomial is approximately equal to 2x to the third, okay? When the absolute value of x is very large. Okay. So if we start with our polynomial, which is what 2x cubed plus 5x squared minus 7x plus 11. Now what we'd like to do is let's factor out x cubed from all terms. And that's going to leave us with a 2 plus 5 over x minus 7 over x squared plus 11 over x cubed. Okay. All right. So now what we'd like to do is we want to consider or let the absolute value of x get very large or tend to infinity. What happens, right? Let's first consider this term here. This by x. So what happens to that guy as that denominator gets bigger and bigger and bigger and goes off to infinity, right? So let's just kind of do a quick little mental exercise, right? So when x is 1, x is 2, what's 5 divided by 2? What's that answer? 5 divided by 10. 5 divided by 100, right? Into that guy. Hopefully you're thinking that it's getting, as the absolute value of x tends to positive infinity, okay? So, yeah, they stopped. Come on. Okay, sorry, we're back. All right, okay, so if we can understand the concept behind that term tending to 0, then it's a similar argument for these remaining terms. So as the absolute value of x tends to infinity, we have a fixed number over ever expanding, we have a fixed numerator over an ever expanding denominator. So all of those terms tend to 0 as the absolute value of x tends to infinity, okay? So then now we have that the given polynomial is going to be approximately equal to x cubed times 2 plus 0 plus 0 plus 0, right? Which is 2x cubed. All right, so what we're saying is as the absolute value of x tends to positive infinity, our polynomial essentially behaves like the power function 2x cubed. So This doesn't give us any information about the middle, but we know as x goes off to the far right or the far left, it's going to behave similar to the way that the power function 2x cubed behaves. Notice that the power function 2x cubed is the leading term of our polynomial, right? Okay, so we have a type version of what we just experienced, and that segues us into the leading term test. So given a polynomial function where the leading coefficient is not 0 and the leading term is a n x to the n, the behavior of the graph of the function as x tends to positive infinity or negative infinity is similar to one of the following 4 graphs and is described as shown in each case. The middle portion of each graph indicated by the dashed lines is not determined by this test. So again, what we're about to see is how our polynomials in the long term behave similar to the power function. Those 4 cases we have for the power function, our polynomial function is going to behave in a similar fashion. All right. So again, here our n is even. Okay. So now we have a positive leading coefficient and n is even. Positive leading coefficient means our graph goes up to the right. If the degree of our polynomial is even, that means the other side does the exact same. So if we go up to the right, we're going to go up to the left. This doesn't give us any information about what happens in the middle, but we know as we go to the far right, we're going up. As we go up to the far left, we're going up. Okay. Next, the leading coefficient is negative and n is even. So negative leading coefficient means our graph in the long term, as x goes up to the right, it falls. And because our n is even, the other side does the exact same. So the other side falls as well. So falls to the right, falls to the left. Okay. Similar to the power function, case 2 in the power function. Now we have a positive leading coefficient, but n is odd. Okay. So again, a positive leading coefficient goes up to the right. N is odd means the other side does the opposite. So if we're going up to the right, the other side is going to go down to the left. This doesn't give us any information about the middle, but we know going to the right or to the left, we know how it behaves. And then the last case, case 4, a negative leading coefficient and n is odd. Okay. A negative leading coefficient means we go down to the right. N is odd means the other side does the opposite, so we go up to the left. Okay, so that's the leading term test. So given a polynomial, once we can identify the leading term, the leading coefficient tells us about the right-hand behavior. The degree of the polynomial tells us about the other side, the left-hand behavior. No information about the middle just yet, but we know about the right and the left. Okay. So now, here, what we like to do is do a quick quiz. Okay. So the first question. Okay. What is I'm going to abbreviate this as the leading term. Okay. Is it A, B, or C? Is it A4? Is it B, this guy, or is it C, this guy? Okay, so what's the leading term? Question number 2. So just kind of, it wouldn't hurt to go ahead and be thinking about this. What is the leading coefficient? Right, so the first one was a leading term. Now we're looking for the leading coefficient, A, B, or C. Is it A, this guy? Is it B, this guy, or is it C, this guy? Okay. Okay, next question, number 3. What is the degree of the polynomial, right? Let me see. Is it okay? Is it -2? Is it 4? Or is it 3? Okay. And then last question, number 4. What is the long-term behavior? Kind of writing shorthand there. We're going to have A, B, C, and D. So is it up to the right, up to the left? Is it up to the right, down to the left? Is it down to the right, up to the left? Or is it down to the right and down to the left? Okay, so we got these 4 questions, right? All right, so let me open up our little quiz sheet that we created last time. We can use to get feedback from the audience to see where everybody's at. You want to take these serious because you never know when I'm going to use this for my attendance, right? So you want to do your best to try to get these correct whenever possible. Let me see. If I go to the poll or quiz, I want the 25 questions. So we got 4 questions. So we're just going to use the first 4 slots, right? So question number 1, question 2, question 3, question 4. Let's take, we'll take 2 minutes. We'll take 2 minutes, right? So we'll take 2 minutes. So I'm gonna just, it's a little timer there that's kind of going. Take 2 minutes to try to answer those first 4 questions. There's a live poll that's available. So give it a go. One minute. $45 seconds. All right, 30 seconds, and I'll show you how to submit this. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2. All right, that's enough. All right. So once you have highlighted your 4 answer choices for those 4 questions, at the very bottom, you got to answer the last 2 questions, all right? So are we in the last 10 minutes of class? It doesn't matter. You can say no or yes. And then how do you feel? Are you confident about what you submitted? So a 10 is you're confident. 0 is dear Lord, baby Jesus, I need some help, right? So submit how you feel. We're going to hit submit. Okay. And I'll give you a few seconds to submit the questionnaire. All right, and again, you don't know if I'm going to do this for attendance, so let's take another 20 seconds. So again, you got to submit those 2 questions at the end so that you can submit the quiz. Uh-oh. I think I might have to mark people as absent. You guys here? 2? Okay, we got some more. All right, we're going to take about 10 more seconds. Oh, I might have to do something for this since people are not engaged. Oh, we're going to have to mark some people absent. No? You don't want to be? You can be marked as absent. It's okay. Yeah, we can mark it as absent. So again, be careful about avoiding these because if you get marked absent enough, you can get booted, and that's gonna take money. You may or may not be able to get back in the course. So it's real money on the line. I know it seems light and playful. All right, I'm gonna close the poll and let's go 10 seconds. Again, to submit it, you got to answer the last 2 questions, and then it'll let you submit. 3. Can we get another one? 2. Uh-oh, I might have to mark some folks as absent. Okay. Okay, we got at least one more. Okay, I'm gonna go ahead and close it. Okay, poll is closed. Ding, 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 ding. Poll is closed. Okay. So again, just be careful because you don't know when I'm going to use this for my attendance. And really, the only way that you get credit, you got to get them correct, right? At least like 50% correct. Okay. So let's review this guy, right? Let's review. Let's see. Let's turn you down a little bit more so I can focus. What's the time? We got a solid 10 minutes, if not more. That was pretty good. Okay, let me get my little answer highlighter thingy going. Let's go style. I want that to be thicker than a Snicker, like that. Fill. I want it lighter so we can see. That's decent. All right, what is the leading term? So the leading term is the term with the highest power. I intentionally tried to shuffle it a bit because sometimes that happens. The leading term, the first one, you should have put B. Okay, B. Let me see, can I duplicate this? So then, what is the leading coefficient? So from the leading term, you can find the leading coefficient should be that -2. In this case, that would be A. Okay. So for question number 2, that would have been A. Okay, not bad. What is the degree of the polynomial? The degree is the highest power on any term. In this case, duplicate. That's going to be C. So the highest power is 3. Okay. So question 3. Okay. And then question 4. What is the long-term behavior, right? What's the long-term behavior? So the leading term test, we have a negative leading coefficient, so it's going to go down to the right. So it has to be either C or D. Has to be either C or D. And then down to the right. And then the degree of our polynomial is a 3, which is odd. So that means the other side does the opposite. So if we're going to go down to the right, that means we're going to go up to the left. The only one that does that is C. Okay. So this was a loaded question, right? You kind of needed to get the first question correct in order to get them all correct. Because the subsequent parts or the subsequent questions were based on that initial one, right? So, and that happens. That happens. So if you make the incorrect like first choice, then everything from there kind of goes sideways, right? Okay. So it was interesting. So again, I don't know that I'm gonna keep announcing, but you got to be careful when I'm doing those poll the audience because I'm gonna start using that for my attendance. And so if we do those and you're not engaged, then to me that's gonna say, oh, we just logged in, but you're like asleep or you're doing something else, you're not really paying attention. So then I'm gonna mark you as absent, right? I probably won't do that today, but just be careful because you don't know when I'm gonna do that. So the best thing is just try to get those right because then you don't want to miss out on you don't want to just give your money away and just this is essentially free stuff. I just need signs of life, right? I just need signs of life. Okay. All right. Okay, so that was interesting. Oh, so these are typos. Let me fix these typos real quick. Oh, did you dial me? No. Why aren't you registering? All right. So let's go like this. Let's go copy and paste. Duplicate. So those are basically, sometimes it doesn't print the symbol properly. So that's what happened there with those. And the correct symbol, I'm doing this color this time. Let's go style like this. Shorten it up just a little bit. Duplicate. So those are supposed to be right arrows. Ooh. Okay. So again, those are just supposed to be right arrows, right? And I think this is just a type version of what we just experienced. Okay. Let me see the time. We got a solid 10 minutes. Let's keep going. So the zeros of a polynomial function, if f is a polynomial function and c is a real number, then the following statements are equivalent. C is a zero of f, but that's the exact same as c is a solution or root of the equation f of x equal to 0, but that's the same as c is an x-intercept of the graph of f. The point c, 0 is on the graph of f, right? So these three statements can be used interchangeably. So whenever you hear us say x-intercept, that's the same as c is a solution or root of the function, f of x equals 0, but that's the same as c is a 0 of the function, right? So again, these three statements are used interchangeably. Okay, it's 3:33. Nice. Okay. Here we're asked to find all zeros of each polynomial function. Okay, since we got a solid 10 minutes, I'll go ahead and do this one. I think it's the first time I'm doing this one with anybody all day. Okay, so here we need to do factoring, right? So this is where factoring comes into play. Again, if you need to bone up on your do a factoring review, in Blackboard, you'll find you go to the box link, like you're accessing our daily notes. And before you click on the notes part inside of box, at the bottom, you're going to see a link that's a folder that says handouts. You'll find two documents that kind of go through factoring there. One is a sheet that summarizes how to approach a factoring problem. The other document is going to be an entire chapter devoted to factoring. So you can find that in box in Blackboard, right? Okay. So if we're working on part A, right? So one of the first questions we ask ourselves is there a greatest common factor, right? Is there something that's common to all the factors that we can factor out, right? And in this case, that would be a yes, okay? So for part A, we can factor out, it looks like all the terms have an x squared, okay? If we factor out x squared, then we're going to be left with x squared minus 2x minus 3, okay? Okay. So then can we factor that trinomial? The goal is to get it to a form this. Because the second sign is negative, that means our signs are going to be opposite. One's going to be positive, one's going to be negative. Because the first sign is negative, that tells us the larger number is negative. Okay? So do we have two numbers that multiply to give us a -3 and add to give -2? I think it's what? -3 and +1? 1 times -3 is -3. 1 plus -3 is -2, right? So then this is the completely factored form of the original, okay? So if we want the zeros, we would set this equal to 0 and solve. So then we would use what's called the zero factor property. When two or more things multiply to give you 0, basically you set each factor to 0 and solve. If we do this from the first factor, the first zero is x equals 0. From the second factor, x equals -1. And the third factor, x equals 3. So when we plug these values of x into the original, these should all make the original 0. So these are the zeros, or the x-intercepts of the original graph. Have you guys registered to vote? Are you going to vote? All right. I remember doing that when I was a student. Who did I vote for? Who was it? Was it? It was. Who was just before Obama? Bush. I think that's the one I voted for. I was at Morehouse, and I've given enough information, so I think you can figure it out. I'll let you figure it out. I think that was the right president. I'm not sure. I don't think it was Obama though. I don't think it was Obama when I think I was already out by then. Okay, so I'm gonna go with that for part A, and then for part B, is there a greatest common factor? No. So in part B, we might try a technique called factor by grouping. So whenever we have 4 or more terms that we're trying to factor, we might try grouping them in different groups and then trying to see can we get to a common binomial factor. So what I'm going to do is group it in this fashion where we have the first two grouped and the last two grouped. Now, if I consider the first two, is there a greatest common factor? Yeah. It looks like we could factor out x squared. All right, from those first two. And it looks like it leaves us with x minus 2. So the hint is, and notice we have a remaining x minus 2 in the second half. So now they both have a common binomial factor, right? Which is mainly that blue part, the x minus 2. So we can factor out the x minus 2 from both terms. And when we do this, we're going to be left with x squared plus 1. All right. So that was a little bit tricky because that 1 is easy to miss. Okay. So that second factor, the x squared plus 1, that one lies entirely above the x-axis. So there's no value of x that's going to make that 0. But that first factor, we have the x minus 2. So from there, we get a 0 of 2. Right. So x equals 2 is the only 0 that we get. Okay, so let's see how do we do. -1, 0, and 3. -1, 0, and 3. And then only 2. Okay. All right. So then we have this thing called the intermediate value theorem. So let a and b be two numbers such that a is strictly less than b. If f is a polynomial function such that f of a and f of b have opposite signs, then there has to be at least one number c between a and b where f of c equals 0. So this is a play on properties of polynomials where they're continuous, smooth, unbroken curves. So given two different x values of a polynomial, if the corresponding y for one has one sign and the corresponding y for the other x value has an opposite sign, then there has to be an x between those two x values. There has to be a c between those two x values where it crosses the x-axis, right? Using the properties of polynomials. That's essentially the intermediate value theorem. And then, it also may be more than 1 0 between those x values. Okay, I'm going to have to use my recording for this one. Okay, so if you want the details on this, use my recordings to kind of fill that in. You have the type version here. And then the zeros of a polynomial function of degree n with real coefficient has at most n real zeros. So whatever the degree of our polynomial is, we have at most that many number of zeros. All right. I'm going to use my recording for this. Okay. If c is a 0 of a polynomial function and the corresponding factor x minus c occurs exactly m times when f is factored, then c is called a 0 of multiplicity m. Right. So when we get our polynomials and we get them in completely factored form, sometimes some of those factors have higher powers, like to the power of 2 or whatever. We call that the multiplicity. If the multiplicity of a 0 is odd, then the graph is going to cross at that x-intercept. It's going to cross the x-axis. If the multiplicity of our 0 is even, the graph is going to bounce off the x-axis at that x-intercept. Okay? So the multiplicity gives us more information about the graph. If the multiplicity is odd, it crosses. If the multiplicity is even, it bounces off the x-axis. Okay? So I'm going to use my recording for this because we're just about out of time. And then turning points, a local max. A local max is like when you're looking at the graph, it's like the top of a mountain. So those little, where our graph turns, we have a turning point, and it's like the peak of a mountain. That's considered, we call that a local max. And then the bottom of a valley, we call those the local minimum. The graph points corresponds to the local max and min values are called turning points. At each turning point, the graph goes from either increasing to decreasing or vice versa. Okay. So in this image, on the left at the point -112, that's our local max. On the right at 2, -15, that's our local min. All right, so this graph has 2 turning points. So given a polynomial function of degree n, we have at most n-1 turning points. We have at most n zeros, but at most n-1 turning points. Okay. And I have to use my recording for this one. Let me give a brief synopsis here. So this can piggyback off of the synopsis we had for graphing rational functions. So like first we might investigate the intercepts. Again, my recommendation is to do the y-intercept first. Oftentimes that one is much easier to find than the x-intercept. Y-intercept, you said x is 0 and solve. A lot of times you just look at it to get the answer. But you might want to investigate the intercepts first. Then you might try your leading term test. So leading term test. So that tells you about the long-term behavior. No information about the middle, but it gives you information about the long-term behavior of the graph. You can check for multiplicity. You can do a test for symmetry. So that's determined if the graph is even, odd, or neither. Even means y-axis symmetry. Odd means origin symmetry. Then a few additional points. Okay. Between and beyond your x-intercepts. I think when we did our rational functions, we said between and beyond the x-intercepts and the vertical asymptote. Here, between and beyond the x-intercepts, right? So once you identify your x-intercepts, if there are any, between your x-intercepts and on either side of the x-intercepts, you just want a few additional points. So choose a couple of x values, find the corresponding y, and then put all this information together. Keep in mind, you could also use the turning points, the multiplicity, but you just want to put all this, so put all this together in a graph, okay? So again, I kind of go through those details in my recording, so you can kind of review that. I'm going to have to leave that for you. And then I'm going to use my recording here. Are there any burning questions before we go our separate ways? Going once, let me check the chat real quick. The chat looks good. Let me see. So on Wednesday, you can anticipate another homework session, but again, more than likely, I'm going to do my whole polling thing, and then I'll keep track of it. So the same way, today where we submitted at the end, we'll probably stop at about 30 minutes into class on Wednesday to tally it up to give feedback on the quiz or whatever, right? So I think we're kind of streamlining it and working out the kinks, right? So if we're gonna, again, you got to get at least 50% correct to get your attendance credit for the day. If you're below 50% correct, then you're kind of at my mercy, depending on my mood, right? And you don't really want to be dealing with my mood because it's really based on nothing. It's just how I feel. So if you don't want to be subjugated to that, then you gotta get at least 50% correct on Wednesday. Okay, you got to fight for your right? Okay. So if there aren't any other burning questions, we're going to go ahead and end the session here. From one beautiful mind to another. Enjoy your evening. I'll make a copy of this available momentarily. And until next time, gentlemen, take care. Peace. That's all. Yes. Wait, you're right to get in the band, everything. Yeah, it's almost there. You can kind of feel it. All right, guys, take care. This has potential now. I can see something with this. Sounds like fun, like a montage. Send it to spot so they can have a copy of the notes and use it. All right, guys.
If it's what I need, and it's a real